Hello and welcome to this lesson of Precalculus, finding zeros of polynomial functions. Today we'll be looking at methods to find all the possible zeros, both real and complex, of polynomial functions. Alright, so the first thing we want to talk about is the rational zero theorem, which states that if I have a coefficient here we'll call a sub n times x to that power of n, and then I keep cascading down powers, so I have another coefficient times x to the n minus 1 power, so this could be like 4, 3, 2, 1, and so on, all the way down to where we get to our coefficient, which we'll call, our constant, which we'll call a sub 0. This is our polynomial function. If we have a polynomial function such as this, the rational zero theorem states that any real zero of this function can be found by taking the fraction p over q, where p is any real factor of your constant in the numerator, and then q is any factor of your leading coefficient of a sub n. So we'll take a look at this with a couple of real examples. So our first example here tells us to list all the possible rational zeros of f of x equals x cubed minus 3x squared minus 2x plus 4, and then determine which ones are zeros. So the first thing we want to do is take a look at our constant, and we also want to take a look at our leading coefficient, which in this case is 1. So on the top of our fraction, all of our possible factors of 4 would be, or I should write that in green, would be plus or minus 1, plus or minus 2, and plus or minus 4. Those are all the possible factors of 4. And then on the bottom, with my leading coefficient of 1, the only possible factors of that would be plus or minus 1. Now, because I already kind of took care of the plus or minus in the top part, each of these does have a plus or minus already. You can see if I divide by plus or minus 1, I'm going to just end up with a bunch of repetitive stuff. So when it all boils down to it, my factors are plus or minus 1, plus or minus 2, and plus or minus 4, because dividing each of those by plus or minus 1 will give me those possibilities. One way I could determine which of these are zeros is I could directly substitute each value into my f of x here. So f of 1 would be 1 cubed minus 3 times 1 squared minus 2 times 1 plus 4. That's going to give me 1 minus 3 minus 2 plus 4. 1 minus 3 is negative 2, and then negative 2 minus 2 would be negative 4, and then plus 4 would give me 0. Now, just to kind of make this a quicker process, I'll just go ahead and put the rest of the work up there so you can see that that actually ends up being our only rational zero. So our possible rational zeros were plus or minus 1, plus or minus 2, plus or minus 4, and then the only zero we had here was 1, because that gave us 0. So let's look at another example here. We've got x cubed minus 2x minus 1. So using our idea where we have the constant over the leading coefficient, all the factors of the constant over all the factors of the leading coefficient, we could have plus or minus 1 basically over plus or minus 1, which means my possible zeros would be plus or minus 1. Now, what I can do instead of using substitution is I can use synthetic division to test both positive 1 and negative 1 for this particular function. So I'm going to put them up top there, and when we cascade this down, we're going to have 1 for my x cubed. Notice there's no x squared function, so I have to put a 0 in for x squared. And then for x to the first, I have -2, and then my constant is -1. I'm going to go ahead and put that in over here as well. And then when we divide these, for this one, we're going to bring the 1 down. 1 times 1 is 1. Add them together, we get 1. 1 times 1 is 1. Add them together, we get -1. And then on this one, we get -1. So my remainder for this ends up being -2. For this side over here, when I do this, I get -1 times 1 is 1. I get -1, and then over here my remainder is 0. And that's what we want. In order to figure out whether one of these is a real 0, if we get a remainder of 0, that tells me that it is. So my possible zeros were plus or minus 1. The real 0 that I have is -1. So that would be my final answer. So go ahead and see how you do with this example problem. So now we want to take a look at an example where the leading coefficient is not 1. For instance, this one where we have 2 as our leading coefficient. And remember, we're just going to do it the same way, where we take the factors of our constant, so plus or minus 1, plus or minus 3, plus or minus 5, and also plus or minus 15. We're going to take all of those over the possible factors of our leading coefficient. So either plus or minus 1 or plus or minus 2. So when we do that, we're going to take each of these divided by 1, which would just be themselves. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15 are all possible zeros. And then we have to take each one divided by 2. So our other possible zeros would be plus or minus 1/2, plus or minus 3/2, plus or minus 5/2, and plus or minus 15/2. So those are all the possibilities I've got, and now we're going to want to figure out which ones would actually be zeros. So how I'm going to do that is by using synthetic substitution, and in order to do that, one of the factors I could test is positive 1, which would mean I'd have x minus 1 is equal to 0. So that's why I'm going to go ahead and just put positive 1 up in my guard tower here. And when I do my synthetic division, I would take 2, -5, -28, and 15. Bring down the 2. I get 1 times 2 is 2, so -5 plus 2, -3. And then I get -3 here. -28 plus -3 is -31. And I'm going to get -31 up here. My remainder is definitely not 0. It's something like -16. So 1 is not a factor, 1 is not a 0 of this function. So to save some time, I'm just going to tell you that -3 does actually work out. So when we put 2, -5, -28, and 15 in, when I bring down the 2, I get -6. Add them together, I get -11. -3 times -11 is -33. When I add those together, I'm sorry, -3 times -11 is +33. And when I add those together, I get +5. and then negative 3 times 5 is negative 15, which does give me a remainder of 0. So therefore negative 3 is going to be a 0 of this function. Now that tells me that x plus 3 equals 0. So then when I divide this original function by x plus 3, what I found out was my other factor is going to be 2x squared. Because if you recall from last lesson, we just take the numbers we get as the coefficients and then reduce the power by 1. So I'm going to have 2x squared instead of x cubed minus 11x plus 5. And then this is just another way to rewrite my original function using those two factors. I can actually factor this further. If I take this second factor, we can use the AC method to tear that down into two more factors, or any other factoring method you would prefer. So what we're going to do is we're going to split the negative 11 up into two parts, and those two parts obviously have to add to equal back to negative 11. Those, to help us factor, those two parts also have to multiply to the product of 2 and 5, which is 10. So two numbers that multiply to give me 10 and add to give me negative 11 are going to be negative 1 and negative 10. So that's what I'll put in for my magic numbers here, negative 1 and negative 10. So we've got x plus 3, and let's group these like so. When I have 2x squared minus 1x, I can take out an x, and I'm left with 2x minus 1. And then on this side, I can take out, what would be best would be to take out a negative 5, because what that does is that leaves me with another 2x minus 1. If I took out a positive 5, these two factors would be opposite. So my final way to factor that out would be x plus 3. I can take out a 2x minus 1 from these two factors, and then I'm left with x minus 5, all equal to 0. Now, we already know from earlier, because x plus 3 equals 0, that x equals negative 3 is a factor. With 2x minus 1 equals 0, we would have to add 1 to both sides, and then divide by 2, which would give us x equals 1/2 as a factor. And finally, with x minus 5 equals 0, that tells us that x equals 5 as a factor. So those are my three factors that end up giving me zeros for my function. So then what I can actually do is I can bring this function up on my graph here, and the graph does seem to show that at x equals negative 3, x equals 1/2, and x equals 5, I have 3 zeros there. So now go ahead and try this on your own and see if you can find the possible rational zeros of this function and figure out which one are actually zeros. So now let's go ahead and take a look at this next example, which is a real world example. And we have the function f of x equals x cubed plus 4x squared minus 2x plus 7 to represent the height of water sitting on a patio to measure the rain. So we want to know on what day the water will reach a height of 10 millimeters. So in other words, if f of x is representing the height, we want to figure out what x value will give us the day of the height reaching 10 millimeters. So in other words, the function f of x has to equal 10. So let's set this up to where we have x cubed plus 4x squared minus 2x plus 7 equals 10. But remember, we're not learning how to find rational tens of a function. We're learning how to find rational zeros. So let's solve this to where my function equals 0. So if I subtract 10 from each side, what I'm going to get is x cubed plus 4x squared minus 2x minus 3 equals 0. So now I have a new function that's actually equal to 0, and I can use what I've learned earlier to determine what my possible zeros of that function are. So let's take all the factors of negative 3, which are plus or minus 1 and plus or minus 3, over all my factors of 1, which are plus or minus 1. So that just gives us the possibilities of plus or minus 1 or plus or minus 3. Let's go ahead and test those out. So if I try, and it'd be silly to try negative 1 and negative 3 because you can't have a negative number of days. So let's just try 1, and if we have to, 3. So if I put 1 in here, I've got 1, 4, negative 2, and negative 3. So do my synthetic division, bring down the 1. I get 5. I get 3. And then that gives me a remainder of 0. So that tells me that 1 is a rational zero of that function. So in other words, day 1 is the day that the rain reaches 10 millimeters. Now go ahead and see if you can figure out a similar problem on your own. As you can probably tell, it would be pretty crazy to test all of the factors of every function all of the time. So one thing that could help us reduce the number of factors we have to test is sort of setting an interval in where those zeros could lie. So if we look at this function, x to the 4th minus 4x cubed minus 11x squared minus 4x minus 12, you can see it to the left and to the right. It seems to tail off into infinity, but our zeros do seem to lie between this point and this point. So I think it's pretty safe to say between negative 3 and 7 is a good interval to try out. So from negative 3 to 7 appear to be where our zeros lie, and then we have a way that we can test both our lower limit and our upper limit to make sure those are the right numbers to choose. So in order to do that, the first thing we want to do is use synthetic division to divide our function by 3 and also by 7. So we're going to use 1 for x to the 4th, go down negative 4, negative 11, again negative 4, and then negative 12. Same thing over here. And bring down my 1. So negative 3 times 1 is negative 3. We get negative 7. 21. We get 10. Negative 30. Negative 34. And for my remainder, I'm going to get negative 3 times negative 34, which is positive 102. And then looks like 90 for that one. Then on this side we bring down the 1. 7 times 1 is 7. We get 3, 21. We get 10, 70. We get negative 66. Actually, that's positive 66. And then when I multiply 7 by 66, I get 462. 462 minus 12 is 450. So that's my remainder on that side. Now there's two different tests for figuring out whether you have an upper bound or a lower bound, to make sure that -3 is in fact a lower bound, what I want to see here is exactly what I do see, where every other number goes positive, negative, positive, negative, positive. So if I have an alternating positive and negative like that, that means I have a lower bound. So -3 works as a lower bound. For 7, to make sure that that's an upper bound, what I want to see is exactly what I'm seeing here, that all the numbers are non-negative. So because of that, that means my -7 is an upper bound. And just so you can see that written out here, as you can see, if c is less than or equal to 0 for every number, then we want to see alternatively non-negative and non-positive numbers, and that's going to tell us that that number is a lower bound. And then if c is greater than or equal to 0, like our 7 was, then we want to see every number be non-negative, and that's going to tell us that c is an upper bound. So back to our example, what that does for us, if we're figuring out all of our possible zeros, we know that we could have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and then plus or minus 12. Those are all my factors of 12, and we could put all of those over my factors of 1, which is this plus or minus 1. So what this limit tells me is that on the negative side anyway, I get rid of -4, -6, -12, because those are all below -3. So the only factors here that are between -3 and 7 would be plus or minus 1, plus or minus 2, plus or minus 3 are both in that interval, but 4, only positive 4 is in that interval, and with 6, only positive 6 is in that interval, and then we totally get rid of the factor plus or minus 12 altogether, because -12 is too small and positive 12 is too big. So this limits my possible zeros down to these 8 numbers here. Looking at the graph again, I think it seems reasonable to think that my only real zeros appear at -2 and 6, which is confirmed by all of the math we did. So just to clarify, my zeros are -2 and positive 6. Now I have an example here for you to try to pick out the interval and also determine the real zeros of the function. So another trick that we can use to determine how many zeros we have and what our zeros are is called Descartes' rule of signs. And basically what that says is we're going to look at our coefficients and see how many times the signs change from positive to negative or negative to positive. If the signs change, say 2 times, that means we could have 2 possible zeros, or we could have any even number less than 2. So we could have 2 zeros, or we could have 0 zeros. If, say, you have 3 sign changes, that means you could have 3 or any odd number below 3. So you could have 3 zeros or 1 0. And then we're going to look at the negative x, the f of negative x, and that's going to tell us the same thing for negative zeros. And I think this will make more sense if we look at an example. So this example asks us to describe the possible real zeros of f of x equals x to the 4th minus 3x squared, or it's 3x cubed minus 5x squared plus 2x plus 7. So if we look at, first of all, determining our positive real zeros, and then later on we'll figure out how to determine our number of negative zeros. Our positive zeros, if we take a look at the function, would be x to the fourth minus 3x cubed. Notice I've gone from positive to negative. That's one sign change, but I'm staying negative for 5x squared. But then I go back to positive for 2x. That's my second sign change. And then I have plus 7. So as you can see, there were two sign changes. That means I can either have two positive zeros or no positive zeros. If we look at f of negative x, so I'm putting negative x into my function, that's going to give me negative x to the fourth minus 3 times negative x to the third minus 5 times negative x squared plus 2 times negative x plus 7. So when I simplify this, f of negative x, negative x to the fourth will still give me a positive number, but negative x cubed is going to give me a negative 1, so I'd end up with plus 3x cubed because it would make that sign opposite. Negative 5x squared still stays the same. Negative 2x changes, and plus 7 still stays the same. So now when I look at sign changes, we've got positive to positive, and positive to negative, so I've got one sign change. Negative to negative, and negative to positive gives me a second sign change. So once again, I have two negative zeros, or I have no negative zeros. So those are my possibilities. I either have 2 or 0 positive zeros, and I either have 2 or 0 negative zeros. So go ahead and see if you can apply that to this example problem and see if you can figure out how many possible positive or negative zeros this function g could have. Now we've got an example where they're asking us to generate our own polynomial when they've given us the zeros. And obviously there's an infinite number of possibilities here. We could write plenty of polynomial functions that could have these zeros of negative 1, 2, and 2 minus I for zeros. But they're asking us to do it with the function of least degree. And when we do this, we're going to do a little trick to make our lives easier, because there's a lot of math involved here, unfortunately. So let's take a look at this. And one thing we want to remember when we have a complex number like 2 minus I is because we're dealing with hopefully a real polynomial, we don't want this I to be tagging along. So the conjugate root theorem tells us that whenever we have a 2 minus I here, for instance, that its root will also be a 0. So it's almost as if they gave us 2 minus I and 2 plus I have to be 0. So really we have 4 zeros we have to maintain. So how we're going to do this, how we're going to create this polynomial, is we're going to use what's called the linear factor theorem, which tells me that I'm going to have a coefficient to start, a, and this could be anything I choose because we're creating this polynomial. So any coefficient a will work along here. So it's going to be easy for us if we just choose 1 for our a. And then what we're going to do is we're going to take x minus each factor. So x minus negative 1 is plus 1, and I should say x minus each 0. So x minus negative 1 is positive 1, x minus 2, and x minus our first complex factor here, which is x minus 2 plus 1, since we're subtracting it. And then we're going to do x minus 2 minus 1, since we're subtracting 2 plus 1. So here are my 4 factors all multiplied together, and remember I said I'm going to make this be 1 so that everything here is going to be equal to itself. The unfortunate part is that I have to multiply this all together. So the first thing I'm going to do is multiply these 2 factors, and then I'm going to multiply these two factors. So to do the first two, I have to FOIL. So x times x is x squared. X times negative 2 is minus 2x. 1 times x is plus x, and 1 times negative 2 is negative 2. So that's my first factor. My second factor is going to be these two multiplied together. So I'm going to have to do each of x negative 2 and I times x negative 2 and negative I. So x times x is x squared. X times negative 2 is minus 2x. And x times negative I is negative ix. Taking the negative 2 times each term, I get negative 2 times x is minus 2x. Negative 2 times negative 2 is positive 4. And negative 2 times negative I is positive 2i. Finally, I multiply the I by everything, and I get ix. I get negative 2i, and I get negative I squared. So I can simplify this quite a bit. Negative 2x plus x is going to be negative x, so x squared minus x minus 2 times x squared. Negative 2x and negative 2x can be combined to give me minus 4x. Negative ix and positive ix will cancel out. And then we're left with our 4 here. And negative 2i and positive 2i cancel out. And we're left with negative I squared. Now, if you remember, I squared is simply negative 1. So really, we're going to put negative 1 in for I squared. 4 minus negative 1 is going to give me a 5. So I've got x squared minus x minus 2 times x squared minus 4x plus 5. Once again, I have to multiply two trinomials together to end up with my final polynomial. X squared times x squared is x to the 4th. X squared times negative 4x is minus 4x cubed. X squared times 5 is 5x squared. And then I'm going to do negative x now. Negative x times x squared is negative x cubed. Negative x times negative 4x is plus 4x squared. Negative x times 5 is minus 5x. And with my constant negative 2 times x squared is negative 2x squared. Negative 2 times negative 4x is positive 8x. Negative 2 times 5 is negative 10. And I can simplify those even more, and I get x to the 4th, in my like terms here, minus 5x cubed. I've got like terms here, here, and here. So 5 plus 4 minus 2 is 7. So plus 7x squared. And then I can combine my negative 5x and my 8x to get plus 3x. And finally, minus 10. So I've created a polynomial that is equal to, well, not equal to anything. It's my own polynomial that has the zeros of negative 1, 2, and 2 minus I in the end there. So all that work to make our own polynomial. And let's see if you can come up with your own polynomial in this next example. So here you go. Go ahead and give that a try. And just a couple of things to note here. With minus 2, multiplicity 2, that's telling you that you've got two negative 2's. So you're going to have to do x minus negative 2 as one factor, and x minus negative 2 as a second factor, and then your x minus 0 there. And don't forget about 3i. You'll need to do the conjugate of that as well, which would be negative 3i. So really in all you've got 5 factors you should include in your linear factorization theorem. Alright, now in this example we're asked to consider this function k of x and then write k as a product of linear and irreducible quadratic factors. Now, what's an irreducible quadratic factor? It's a quadratic function that can't be factored any further, something like x squared plus 1, because that's not a difference of squares with real numbers. But we're going to look at, in this particular example, we're going to look at a way that we can actually factor that down. But before we do that, let's write this k of x as a product of linear and whatever factor we end up with at the end. So when we look at my graph, I have it all written in here, and if I go ahead and look at it, it looks something like this. And as you can see, it appears that I have potentially zeros at negative 3, negative 2, and positive 4. To make sure here, we can go back and think about Descartes' theorem, where if I go by the number of sign changes, in my positive x, I have, no sign change there, but I have a sign change from positive x fourth to the negative 13x cubed, and then I stay negative through to the end. So I have one total sign change here. That means I can have one positive 0. And it appears that that positive 0 I have is 4 in this case. So let's try it. Let's use synthetic division to see what that turns out. So we'll put 4 in, and then my coefficients of this function would be 1, 1, negative 13, negative 23, negative 14, and negative 24. When I divide that out, I'm going to bring the 1 down. 4 times 1 is 4. It gives me 5. 4 times 5 is 20. Adding those gives me 7. 4 times 7 is 28. Adding those gives me 5. I get 20. Adding those gives me 6. And finally I get 24, which verifies that I have a 0 there at 4. Now, my other supposed factors seem to be negative 2 and negative 3. So let's just try one of those. We'll put negative 2 in here for my what's called my depressed quadratic that I brought down. So I'm just going to divide this to see if I can divide it by negative 2. So bring down my gate. 1 escapes. Negative 2 times 1 is negative 2. I get 3. Negative 2 times 3 is negative 6. I get 1. Negative 2 times 1 is negative 2. I get 3. And then I get negative 6. Again, I get 0 for my remainder. Looks good. Let's just test my third suspected factor. Negative 3. I should have wrote that a little bit higher so it matches our depressed function. So I put negative 3 here. I bring down the 1. Negative 3 times 1 is negative 3. I get 0. I get 0, 1. Negative 3 times 1 is negative 3. My remainder is 0 there. And what's going to happen is we are going to end up with a quadratic here because our original was x to the 5th, which made our first division x to the 4th. Our second division answer x to the 3rd. And our third factor became x squared. So that will be a quadratic that we cannot reduce. So in order to write all these factors, first I had x minus 4 as a factor. I had x minus negative 2 or x plus 2 as a factor. I had x minus negative 3, which is x plus 3 as a factor. And I ended up with x squared and a constant of 1 as a factor because 0x we don't have to write. And that all to find the zeros, we could set that equal to 0, but really it's our k of x rewritten. So this is my answer for the first part, but then of course the book's going to ask us to do a little bit more. Now if we absolutely have to write this function as a product of linear factors and not just linear and quadratic factors, we're going to have to bring in imaginary numbers, because there is no way to factor this out into real numbers, but we can rewrite it in such a way that it will give us a difference of squares of imaginary numbers. So if you remember, to have a difference of squares, we'd like to have x squared minus -1, and we're going to consider this -1 a square of something. And of course we know that -1 would equal the square root of -1 squared. We also know that the square root of -1 is I, so -1 would equal I squared. So we could rewrite this whole thing as x squared minus I squared. So to factor that out, we would get x plus I, x minus I, and we can just rewrite this whole thing as all linear factors. So x minus 4, x plus 2, x plus 3, and then x plus 1, x minus 1, that's equal again to our k of x, and that's what they were asking for. It's all linear factors, so that's my answer. Now finally, the last part of this example is they want us to list all of the zeros of k. Simply each of these 5 factors that I just mentioned, if we set them each equal to 0, that's going to give me positive 4, negative 2, negative 3, and this should be an I, by the way, but that's negative I and positive I are my 5 zeros. So here's another example for you to try. You're going to want to rewrite that that k of x function as the product of linear factors and linear factors only. So in our very last example here, we're just taking a look at how we can use synthetic division with complex numbers the same way we did with real numbers in the past. So this is just taking the function p of x there, and we know that one of the factors, or I'm sorry, one of the zeros is 2 plus 5i. That means that one of the factors would have to be x minus 2 plus 5i to give us 0. So because of that, we're going to put 2 plus 5i in our watchtower up here, and just like before, we're going to put all of the factors in, so all of the coefficients in. So 1, negative 6, 35, negative 50, and negative 58. And we will put our fence up, bring down the 1, so 2 plus 5i times 1 is going to give me 2 plus 5i here. When I add a real number with a complex number, I'm adding the real part, so negative 6 plus that gives me negative 4 plus 5i. And then things start to get a little crazy. 2 plus 5i times negative 4 plus 5i is going to give me negative 8 for my front terms. Outer will give me 10i. Inner will give me negative 20i. And last will give me 25i squared, which is negative 25. Negative 8 and negative 25 give me negative 33. 10 and negative 20i give me minus 10i. So we've got now negative 33 minus 10i. 35 plus negative 33 is positive 2. So we've got 2 minus 10i. We've got to do the same thing for 2 plus 5i times 2 minus 10i. And we get 4 minus 20i plus 10i minus 50i squared, which is going to be plus 50. So that gives me 54 minus 10i. So 54 minus 10i is going to give me 4 minus 10i. And then one last time, 2 plus 5i times 4 minus 10i. So we get 8 for my front terms minus 20i plus 20i. Those cancel out. And my last term I get minus 50i, which is going to be plus 50. So I get 8 plus 50, which is 58, which lovely gives me a remainder of 0 after all of that. Now, if you remember earlier, we said that if 2 plus 5i is a 0 of p, then we also know that 2 minus 5i is a 0 of p. So what I can do is I can take this 2 minus 5i and divide my depressed function here by that. So let's make another fence here and bring down the 1. 2 minus 5i gives me 2 minus 5i. When I add those, I get the complex, the imaginary part cancels out. So I have negative 4 plus 2, which will give me negative 2. So 2 minus 5i times negative 2 is negative 4 plus 10i. Again, my imaginary part goes away. I have 2 plus negative 4, which is negative 2. And one more time here, 2 times negative 2 is negative 4. Negative 5i times negative 2 is plus 10i. Those are opposites of each other, so they will cancel out and give me 0. And I have my last factor. So my first factor would be x minus 2 plus 5i. My second factor would be x minus 2 minus 5i. And then I'm left with my third factor of, we brought this down from x to the fourth, x cubed, now x squared. So we'd have x squared minus 2x minus 2. So those are my three factors of my original function p. The only thing is that they asked for a linear factorization, not just a quadratic factorization. So here we have to break this quadratic down into more factors that are linear. And we can factor it out a number of ways, but I can't really come up with two numbers that multiply to negative 2 and add to negative 2. So let's use our good old quadratic formula. So x equals the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. So when we do that with this particular function, or this particular quadratic here, we're going to have positive 2 plus or minus the square root of b squared, which is 4, minus 4 times 1 times negative 2 all over 2 times 1, which is 2. So that equals 2 plus or minus 4 times, let's see, negative 4 times 1 times negative 2 would give me positive 8. So we're looking at positive 8 and 4 to give me 12 over 2. So it looks like my two factors are going to be 2 plus the square root of 12 over 2 and 2 minus the square root of 12 over 2. If I wanted to, I could rewrite this as 2 plus or minus, 12 is 3 times 4, so we can take a 2 out, and then the 3 is left over 2, and then 2, 2, 2 cancel out to 1, 1, 1, and we'd have basically 1 plus or minus radical 3. So I've got one factor, two factors, and then two factors here. So how we could write that as all as linear factors is x minus 2 plus 5i, x minus 2 minus 5i, x plus, I'm sorry, I need to say minus there, x minus our factor here, 1 plus radical 3, and then x minus our other factor, 1 minus radical 3. So those are all four of our factors written out in linear form. So I promise you this lesson's finally over. There's one more question to answer. Find all the complex zeros of this function h of x. See how you do. Thanks for watching. Thanks for enduring all of that math. And good luck. Ask me if you have any questions on this lesson.